This conference will now be recorded.
Hello everyone. Methods of preparation for amines. 5 methods we have already discussed. Now under 5 method, if you look the previous slides. So this is number 5th point, which is from alkyl halide. So starting material is alkyl halide, and under this heading we have the first reaction Gabriel halimide synthesis, which is A, and then we have B, which is Hofmann ammonolysis, and today we will start from C. Here also alkyl halide is the starting material. So 3 different types of reactions. Common thing is in all cases alkyl halide is the starting material. Now alkyl halide will be treated with sodium azide. Sodium azide is this compound NaN3. Na we know plus, okay, that is positive, single positive charge, that is the oxidation state. That means negative charge that is present over nitrogen, it is single negative charge. So Na plus N3 minus, this is known as azide ion. Name of the compound sodium azide, followed by reduction using lithium aluminium hydride. So first we have taken here methyl bromide, which is alkyl halide. You are treating it with NaN3. Br is replaced by the ion N3 minus. We are getting methyl azide. You can also consider the general expression, which will be RBr, or it may be Rx also. RBr, it will be converted to Rn3, and then reducing agent use lithium aluminium hydride. So finally the fate of N3 will be NH2, and there are total 3 nitrogen, 2 nitrogen will be removed in the form of nitrogen gas. Final product methylamine. So in this process the final product you are getting is 1 degree amine. So this is a method by which you can prepare primary amine, 1 degree amine. This is number 5th method. Number 6, ammonolysis of hydroxyl compounds. Obviously now the starting material is hydroxyl compound, that is alcohol. When vapor of an alcohol and ammonia gas passed over alumina, or you can take W2O5, which is oxide of tungsten, or you can take silica. Temperature is very high, 4000 degrees centigrade. All types of amines can be formed, and this method, there is a specific name for this, Sabatier-Maillet method. Okay, so what we are doing in this case, we are starting from ethanol, C2H5OH. You can take any of these, alumina, WO5 or silica, in presence of ammonia obviously. So this OH, now it is replaced by NH2 group. Okay, so in this case you are getting 1 degree amine. But if your purpose is to make 2 degree amine, what you can do, rather than stopping the reaction at this portion, you can further continue, and for that you have to add another mole of ethanol. Now another hydrogen of C2H5NH2 is replaced by another ethyl group, which is basically coming from C2H5OH. So as if here C2H5NH2, it is acting as nucleophile. Just in the first step, ammonia itself is the nucleophile. It is attacking at this carbon and OH is removed. Now the product itself is nucleophile and it is attacking the C2H5OH molecule, and we are getting diethyl amine. Then this is 2 degree, but if you want to get 3 degree, another molecule of C2H5OH you have to add. Then you are getting finally 3 degree. So it depends on our purpose, whether we want to make 1 degree, 2 degree or 3 degree. Depending on that, we have to take accordingly the mole ratio of ammonia and C2H5OH must be present. If you want to stop the reaction at this position, then C2H5OH should not be taken in excess. It should be 1:1. Okay. So ammonolysis of hydroxyl compound. So the definition of ammonolysis is basically when you are using ammonia molecule to replace some other group. In this case, it is OH. So it is ammonolysis of hydroxyl compounds. Which of the following amines can be prepared by Gabriel-Thalamide reaction. Gabriel-Thalamide reaction, we use thalamide as the starting material, and remember, in this case, we can make only 1 degree amine. Starting material thalamide, as I have said, and here, if we see the reaction, you will see that starting material is again Rx. Thalamide is also starting material, but thalamide is basically the source of nitrogen. It will provide the nitrogen because you are making amine. You need nitrogen. Starting material is Rx, that is alkyl halide, but another reaction partner is also there, which is thalamide, which is the source of nitrogen. Options, if you see, N-butylamine, which is basically 1 degree amine. Then we have triethylamine, which is 3 degree. Neopentylamine, this is 5 carbon chain amine. This is also 1 degree. And tertiary butylamine, that means tertiary butyl group. Then there is amine. This is also 1 degree. Okay. Now, if we look at the reaction, see, thalamide, this is the structure of thalamide. This reaction we have already seen in the last class. Again, we are seeing it because this question is all about thalamide. Fine. Thalamide, then we are treating it with alcoholic KOH. That is, this H will be replaced by potassium. So now it is sodium, potassium or sodium also possible. Salt of thalamide. Next, Rx, which is the actual starting material. This Rx will be converted to finally RNH2. We are getting this N minus, it is attacking this R, and X is removed. So when X is removed, we are getting this type of structure, which is N-alkyl thalamide. And finally, we have to do hydrolysis under basic condition. This bond will be broken. So from this part, you will get RNH2. So what you are getting? You are getting 1 degree amine. Fine. So here correct option will be 1 degree amine, which is N-butyl amine. Fine. Next question, which of the following reaction is an example of ammonolysis? Ammonolysis we have just discussed, and not necessary that in ammonolysis your starting material it has to be hydroxyl. No, the specific reaction that we have discussed in the last slide, that is ammonolysis of alcohol specially, but it's not necessary. What is necessary in when you are saying ammonolysis? Ammonia must be there. Now look at the options. First one is benzoyl chloride, PHCOCl, benzene ring COCl plus aniline. We are getting amide. Then C6H5Cn and C6H5CH2CH2NH2. That means it is PHCH2CH2NH2 like this. Then the third one, aniline C6H5NH2 in presence of acidic condition. We are getting NH3. This is actually plus. So this is nothing but the salt of aniline. And the last reaction, you have some C6H5CH2Cl. That means you have this molecule, benzyl chloride. Benzyl chloride, when treated with ammonia, then what you will get? You will get C6H5CH2NH2. That means PHCH2NH2. So net reaction is that what you are doing, you are replacing Cl, that is the halide, with NH2 in presence of ammonia. So this is actually the ammonolysis reaction. And if you consider the definition, the process of cleavage of CX bond by ammonia molecule, that is actually ammonolysis, but not necessarily it has to be halide, it may be COH also. In that case also you can say this is ammonolysis, but ammonia must be present, otherwise how it will be ammonolysis. So keeping all these factors in mind, this will be the correct option. Okay. In last question, one thing I forgot to mention, tertiary butylamine, this is actually 1 degree amine, but this is 3 degree. These two are also actually 1 degree, but you have to remember that as here the nucleophile, this is actually the nucleophile. Sorry, not this one. The actual nucleophile is this molecule. This is the nucleophile, and nucleophile, if you look at the structure properly, this is very sterically hindered. Now, if this R group is very large in size, what will happen? the negative charge, when it will attack here, that will be statically hindered. So that is why by this process you can make simple 1 degree amine, not just any 1 degree amine. So this 1 degree amine, N-butylamine, which is very simple, 4 carbon linear chain, 1 2 3 4, and then there is NH2. But if you consider neopentyl, there is 5 carbon and some branching, or tertiary butylamine like this, that is Me3C and then NH2, which is very statically hindered. So reaction, though it may happen, but yield will not be very good. You can make only very simple structure, primary amine, by Gabriel Thallimine. So that is why first option we have chosen. In the reaction of hypobromite with amide, this problem is also based on the synthetic methods of for the preparation of amines. Hypobromite reaction with amide. Now this reaction is basically Hofmann degradation reaction. Remember, in Hofmann degradation what we have done? We start from RCO NH2, which is nothing but amide, and we treat it with bromine. In basic condition it may be NaOH or it may be KOH, and in the medium hyperbromide is produced, which is NaOBr, and this reacts with amide. So it can be mentioned as hyperbromide or it can be mentioned as Br2 plus NaOH or KOH. So both are actually fine. Br2, NaOH or KOH. This is actually the source of hypobromite. So any of this, if it is mentioned, it is actually means that it is talking about Hofmann degradation reaction. So in Hofmann degradation reaction, we use this type of reagent, and 1 carbon is lost. Finally, we get RNH2, which is 1 degree amine. So this is Hofmann degradation. Now in this case, the carbonyl carbon which is lost, that is this carbonyl carbon. The question is asking, in this reaction, the carbonyl carbon which is lost, it is lost in which form? Is it carbonate? Option 1. Is it bicarbonate? Option 2. Is it carbon dioxide? Option 3. Or it is carbon monoxide, that is CO. So which of these will be correct? Remember, this is the reaction in general form, RCONH2 in presence of bromine or NaOH, or hyperbromide, both are actually same thing, because in the reaction medium in C2 it will be generated. This is the final product. And remember, here this CO is removed. Detailed mechanism, even if you don't want to go, it's fine. You just have to know what is the side product. So what is the fate of CO? How it is removed? It is removed in the form of sodium carbonate. If it is potassium, it is potassium carbonate, but it is carbonate. Fine, because you can see in other side products there is no mention of carbon, so it must be carbonate. So keeping this in mind, carbonate should be the correct option. Next question. A reaction of 0.1 mole benzylamine. Benzylamine means this is also aliphatic amine. Don't think this is aromatic, because NH2 group is not directly attached to pH. It is attached through some carbon, CH2. So it is aliphatic. You are treating it with bromoethane. Bromoethane means ethane is C2H6. Just replace one H with Br. So it will be C2H5Br. So you have taken these two, 0.1 mole benzylamine. Remember, you are treating it with bromoethane, which is nothing but alkyl halide, and it is giving you 23 gram of benzyl trimethyl ammonium bromide. Benzyl trimethyl ammonium bromide. If you are treating these two molecules together, then remember this H can be replaced by C2H5, which is coming from C2H5Br. Now you have total how many hydrogen? You have total 2 hydrogen. So these 2 hydrogens can be replaced with 2 C2H5Br. That means it is 1:2. But remember, once it is replaced by C2H5, now the structure of the molecule will be like this: PHCH2N, ethyl group, ethyl group. So this is 3 degree. But remember, if you now have another molecule of C2H5Br, then also reaction is possible, because it has still a lone pair. So C2H5Br or in general if I write RBR, both are fine. So it can again attack this R. That means now R will be attached to N. In our case, R is ET. But when it is attached to N, now it will be positively charged because total 4 bonds surrounding nitrogen. Valency is cross. That is, I mean, trivalency is the valency of nitrogen if it is neutral, but when it is 4, it will be positive. But this attack is possible, right? You have started from 1 degree amine, you are treating it with bromomethane. So final product you are getting benzyl trimethyl ammonium bromide. Fine. Sorry, it is bromomethane, not ethane. So it should be CH3, not it is methyl. Okay, it still means it is methyl. Fine. So that is why the final product, look at the name, benzyl group trimethyl. That means 3 methyl group, 1 benzyl group attached to ammonium. This is positively charged. This positive charge is balanced by bromide ion. So that is why the name benzyl trimethyl ammonium bromide. Now in this case, the number of moles of bromomethane that will be consumed, suppose it is expressed in this way, n into 10 to the power minus 1. When n you have to round off to the nearest integer. It is also mentioned that 23 gram of benzyl trimethyl ammonium bromide. Okay. Now see, though this value is given, but you don't have to bother about this value because you know what is the starting amount of benzylamine, which is 0.1. Now from 1 mole of benzylamine, maximum 3 molecules of CH3Br can react. That is the maximum capacity. So when it is 0.1 mole, then 0.1 into 3, that means 0.3 moles of CH3Br can be reacting with this PHCH2NH2. So it is always 1:3. But as you have to express it in terms of n into 10 to the power minus 2, that means 0.3 when you express in this form, it will be 3 into 10 to the power minus 1. So answer should be 3. Now look at this. Starting material which you have taken 0.1 mole. This is the first molecule of CH3Br. You are getting 2 degree amine. Then another molecule of CH3Br. Now you are getting 3 degree amine. Then the third molecule of CH3Br. Now you are getting some salt, and this positive charge, there is already presence of Br minus in the reaction medium. So the whole structure, that is a neutral structure, you can write in this way. So benzyl trimethyl ammonium bromide, this is actually this final molecule. So per mole of PaCH2NH2, you are using 1, 2, 3, total 3 moles. So it is 1:3. The ratio of amine and alkyl halide 1:3. Finally, you are getting some salt and reaction is stopped. Further reaction not possible. So if it is 0.1, final product will be 0.3, but you have to express it in terms of n into 10 to the minus 3. That means 3 into 10 to the power minus 1, which is nothing but 0.3. So n value, if you compare, it will be 3. Answer here is 3. Round off to nearest integer. Though we don't have to round off here, it is simply 3. Okay. And one interesting thing, see, don't waste your time by unnecessarily doing calculation. Though here atomic masses of carbon, nitrogen, bromine, and these 3 and hydrogen, all these are given, but you can calculate it. That is, you can do the calculation for molecular weight of the final product, but that is actually not required. If the starting mole number are not given, then maybe the calculation is necessary, but in this case calculation is not necessary. It is simply wastage of time. So just because all the informations are given, it is not necessary always that you have to utilize all the information. Maybe some informations are extra. It is just given to make us confused, right? Fine. So answer is 3, and this 23 gram, this information is redundant. It is not required. After finishing methods of preparation and related problems, next is physical properties. Physical properties of amines. Physical state and smell. If you consider lower aliphatic amine means where carbon number is C1 or C2. Very simple. They are colorless gases. For example, CH3 NH2 methylamine or ethylamine, and have ammonia-like smell, because ammonia, that is the simplest amine possible, where you do not have any alkyl group. This is the simplest structure of amine possible. And when you are considering lower aliphatic amines, that means C1 or C2, obviously their structure is very simple, just like NH3, very close in structure to ammonia. So that is why their nature, smell, it is ammonia-like. When it is 4 or more carbons, as you are moving from 1 2 carbon towards high value, now gradually from gaseous state it is becoming liquid and volatile liquid. That means not very high boiling liquid, volatile, low boiling point. And there is a fish-like smell. Okay, so that is all about aliphatic amines. If it is aryl amine, though aryl amine will be discussed separately, that is their structure, hybridization, chemical properties, basicity, everything will be discussed separately. But here also we have this point, that is aniline and aryl amine, they are usually colorless. That is, aniline is this one. That is the simplest aryl amine possible. NH2 group attached to aromatic ring. But other aryl amines, suppose naphthylamine, where you have 2 benzene ring, then NH2, that is also possible. That is also aryl amine. So for aromatic amines, that is simple aniline or other aryl amines, they are usually colorless. But if you keep it in open air for long time, there will be oxidation, because in air, when you are keeping it for long time, oxygen is present in air, and that oxygen can react with it, leading to oxidation and some color generation. But if it is in pure condition, it is colorless. Physical state and smell we have seen. Now it is solubility in water and also in organic solvent. Lower aliphatic amines, that means low molecular weight, they are soluble in water. And remember, in 1 degree amine, if you count number of NH bond, total 2 NH bonds are there, and these hydrogen are active because they are directly attached to electronegative atom. They can form hydrogen bond with water molecules, but solubility will be decreasing as molecular masses of amines are increasing, because there is increase in hydrophobic part. So in general, if I write R NH2, so NH2 part is fixed. In R, suppose when it is methyl, it is very simple, but as you are moving to ethyl, propyl, butyl towards high value of hydrocarbon chain, obviously the hydrophobic alkyl part is increasing. So that is why, though hydrogen bond formation is still possible, because still you have 2 NH bond, but though it is possible, but still the other factor, which is hydrophobic part, is increasing. Because of that factor, ultimately overall effect is that solubility will decrease. Amines are insoluble in water, but readily, that is in general, if we see, though some lower aliphatic amines are soluble, but most of the amines, they are not soluble in water. So that is, it is mentioned here, insoluble in water. But compared to water, if you take some organic solvent, that is benzene, ether, etc., now solubility is quite good. Here we have this general structure of amine. We have taken R3N. Now this R, it may be H, or it may be some alkyl group, some aromatic ring, and the lone pair which is present over nitrogen, that is taking part in hydrogen bond formation with the hydrogen of water molecule, because this H is attached to oxygen. So this is one type of hydrogen bonding that is possible. And suppose if any of this H, any of this R, if it is H, suppose if it is R N H H, so this H also can take part in bond hydrogen bond formation with, now it is with oxygen. It is possible, oxygen of which is coming from water molecule. So that is also possible. The picture that you are seeing here hydrogen of water molecule is interacting with the lone pair, but ultimately it is interacting with nitrogen basically. But the reverse is also possible, that is H of amine, if H is present in amine, if it is not 3 degree amine, because in 3 degree amine you do not have any NH. If it is not 3 degree, then NH will be present, and that is also interact with, that is hydrogen bond formation is possible with oxygen of water molecule. So this is solubility. After solubility, boiling point. Because of polar nature of primary and secondary amine, they can form intermolecular hydrogen bond. That means hydrogen bond between two individual molecules of amine. But this type of hydrogen bond you cannot expect in case of 3 degree, because in this case there is no NH bond, and that is why how hydrogen bond will be there. But if you consider 1 degree, you can see this nitrogen of one amine molecule, it is interacting with the hydrogen of other amine molecule, and in this way this nitrogen, third amine molecule, fourth amine molecule, so there will be extended chain, right? Similarly, when it is 2 degree, this is also possible, though it will be to some extent reduced, because now the number of NH bond is decreased. In this case you have 2 NH bond, here you have 1 NH bond, and in 3 degree there is 0 NH bond. So as the number of NH bonds are decreasing, hydrogen bond formation intermolecular, here we are not talking about hydrogen bond formation with solvent, that we have already seen, that you have to consider when it is solubility. But now we are talking about boiling point. Boiling point means what? From liquid state it is going to vapor state, so you have to bring the molecules as far as possible, because in liquid state they are close to each other, in gaseous state they are far from each other. Okay, so you have to break this interaction between two individual amine. Higher is the hydrogen bond, more energy you have to provide. So you can expect that 1 degree amine, provided the other conditions are same, that is R, the nature of R is same. Under that condition, 1 degree should be having higher boiling point. Now we will compare boiling point of amines with some other type of molecules. For example, alcohols, alkanes, and remember, molecular weight must be fixed. And this thing, not just in this chapter, we have also seen in other chapters. Whenever you compare boiling point of different types of molecules, amine, carboxylic acid, alcohols, whatever, you have to fix the molecular weight, because molecular weight, if it is not same or close, then with increase in molecular weight, boiling point will also increase. So that is why comparable molecular weight. In number 1 and 2, we have taken amine. This is 1 degree amine, this is 2 degree amine, this is 3 degree. Molecular masses same. Now look at the values. 3 degree amine 277, 308, 321. So maximum is for 1 degree. So now we are comparing among different types of amines. But now if you look at the alcohol, which is also having almost same molecular weight, 355. So which is even crossing the value of 1 degree amine. And for alkane, it is very low, even lesser than the 3 degree amine, because in alkane there is no such polarity, but in amine you have polarity and NH bond. In OH also you have polarity. But why alcohols are higher? Because if you compare the polarity of NH bond and OH bond, obviously NH bond is less polar, so that is why boiling points will also be less interaction, so boiling point is also less. So in this way you can compare amines with alcohols. Amines have lower boiling point than alcohols. And because electronegativity of nitrogen is lesser than oxygen, so NH bond is less polar. Fine. So boiling point, if you compare among 1 degree, 2 degree, 3 degree, keeping the nature of alkyl groups same and molecular mass very that is almost close or same. If you compare, you will see 1 degree, then 2 degree, then 3 degree. And in general, if you compare amine and alcohol, obviously alcohols will be having higher boiling point. Boiling point of various amines follow this order, as I have said, 1 degree, 2 degree, 3 degree, and molecular masses, they should not vary much. Now we will see these different types of 1 degree amine molecules. If you look at the molecules, all are basically 1 degree. All are primary aliphatic amines. We have boiling point in blue color in the left hand side of the molecules, and solubility information in the right hand side, which is in orange color. And when we are saying solubility and the values you are seeing, so these are the values for solubility. Here it is written miscible, that means it is high solubility, so values are not mentioned. But when gradually it is decreasing, unit is gram per 100 gram of water. So if I'm saying it is 0.13, that means for this molecule 0.13 gram is the maximum solubility, is the maximum amount you can dissolve in 100 gram of water. Boiling point, if you move from the molecule 1, 2, 3 to 5, here number of molecules are given like this 1, 2, 3. Boiling point steadily increases as the length of the carbon chain increases, and that is expected because of incremental rise in intermolecular forces. So the hydrophobic part is increasing, van der Waals interaction, which is responsible for hydrophobic region, that will also increase, and boiling point will also increase. -6 degree, then 17, 49, 78. Okay. And if you look at the solubility, solubility would be expected to fall because, as we have already seen in the solubility slide, miscible, miscible, miscible. But once you reach this molecule, hexylamine, now it is drastically decreased. So there is dramatic reduction from hexylamine onwards because of increasing hydrophobic part. Solubility is basically because of this NH2 group, right? NH2 group is fixed. You are not changing that. You are just changing this carbon number in the chain. So keeping the polar part fixed, you are just increasing non-polar part. So that is why there is reduction in solubility. 1.2, then 0.5, lesser than 0.5, 0.13, lesser than 0.4. Okay. So in this way we can compare boiling points and also solubility, and all these are primary amines and also aliphatic amines. Amines. So whenever in organic chemistry we talk about basicity, amine molecules come first in our mind, right? Now why they are basic? They are basic because they have lone pair over nitrogen, and these lone pairs can be donated. Now it can act as base when these lone pairs are donated to some proton, that is, it is capturing some proton. But it can also be nucleophilic. Nucleophilic means now the lone pair will be donated to some electron deficient atom which is not hydrogen, and mostly in organic chemistry it is carbon. So that is the difference between basicity and nucleophilicity. But in both cases there must be some negative charge present. So in this case there is lone pair present. They will react with acid, there will be some salt formation, and when they are acting as nucleophile they can also react with electrophile. Okay. So for example, when we have discussed methods for preparation of amines, remember, suppose you have taken any amine which is RNH2 and you have some alkyl halide R prime X. So in this case the lone pair over nitrogen, it has attacked this R, and as a result this X is removed as a leaving group. That means here RNH2, the lone pair over nitrogen, is acting as nucleophile. So in this way it can act as base or nucleophile. So rather than taking Rx, that is alkyl halide, suppose you have taken some acidic proton is present, and now this lone pair can also attack. So in this case it is base, in this case it is nucleophile. That is the difference. Next we will see expression for basic strength of amines. pKa we use when we compare acidity, that you have seen in carboxylic acid chapter. But now we are talking about basicity. So now we will use another term which is pKb. Suppose you have taken this amine RNH2 in water, this lone pair, it will be capturing this H of water. It will be converted to this type of salt, and HO minus will be there. Now Kb value for this reaction, it is concentration of protonated amine, concentration of hydroxide divided by concentration of unreacted RNH2, that is undissociated RNH2. And water is not considered because it is present in excess. So this is the basicity constant Kb. This equilibrium will exist in aqueous solution and it lies far to the left. Hence, it means what? The equilibrium, if it is mostly remaining in the left hand side part, that means it is very weak base. Not like NaOH. NaOH is inorganic base. It is very strong, we know, NaOH, KOH. But RNH2 is also basic in organic chemistry, but it is not so basic as NaOH. So for NaOH, you can expect complete dissociation, but in this case, it is not complete. That means if the value of concentration for these two terms in numerator, if it is very high, low, not high, if it is very low, that means equilibrium is far to the left. and concentration of undissociated in RNH2 is very high. So denominator is high, numerator low. That means overall Kb value is not very high. And if it is Kb, then pKb will be just like pKa we have seen, negative logarithm of Kb. So when Kb is very high, that means it is a very good base. Because of this negative sign, pKb will be very low, inverse relationship. Okay, so lower is the pKb value, higher is the basicity. Here we have some list of pKb values. So these three amine 1 degree, 2 degree, then 3 degree. Look at the pKb values 3.38, 3.28, 4.22. That means from this experimental result we can say here 2 degree is maximum basic. After that it is 1 degree and then it is 3 degree. I'm just talking about experimental observation. What is the reason behind that? We will come to that point later. But this is the observation. Then again we have taken ethylamine, diethylamine, triethylamine. In the first column it is methyl, alkyl group is methyl, but now it is ethyl. In this case also 2 degree is maximum basic, after that it is 3 and then it is this one, 1. Then we have taken benzylamine, pH CH2NH2, 4.74, that means lowest pKb, highest basicity. Then we have C6H5NHMe, one of the H you have replaced with methyl and other H is also replaced with methyl. So as you are increasing alkyl group, what is the effect on pKb? It is 8.9 to 9.3. So that means compared to the first one, now it is increased. So basicity is decreased. Fine. Now different factors are related for when you try to find explanation for this type of order of basicity. Now these factors, total 3 factors are there. But remember, you also have to be clear about the fact that when you are comparing basicity, whether you are doing it in aqueous medium or you are doing it in gaseous phase. Because when it is gaseous phase, solvent effect will not be present. Solvation effect or solvent effect, whatever. But when it is aqueous, solvent effect will be present. So in gaseous phase, no solvent effect. In aqueous, you have to consider solvent effect or solvation effect. So one by one, we'll see these points. When you compare the basicity, basically you have to take care of these 3 factors. Inductive effect, that is plus I effect, which is coming from alkyl group, positive inductive effect. Then solvation effect, which is coming mostly from water because we consider basicity mostly in water. And steric hindrance. That means the alkyl groups, if whether they are very large or not. So all these factors, there will be some that is individual effect. But when you consider the overall effect, then it may be completely different. So sometimes it may happen that the result that you are, that is the conclusion that you are getting by considering only inductive effect, that conclusion is not matching with the observation that you are getting by considering only solvation effect. Okay, but when you combine this, you can explain why experimental results are so. First is inductive effect. When a plus I group like alkyl group is attached to nitrogen, obviously electron density will increase and it will make the electron pair readily available for protonation. So if this logic is correct, then compared to ammonia, alkyl amine, see this is ammonia molecule, the first one, it is donating lone pair. Now we are getting NH4 ion. This is nothing but NH4 plus ion. And when it is 1H is replaced by R, now it is 1 degree amine and plus I effect is operating. So this lone pair donating tendency will increase. Here also you are getting salt, which is R NH3 plus salt. So this is alkyl ammonium ion. So obviously in second case, if you consider this plus I effect, in the second case basicity should be high. That is the tendency to capture proton, that will be high. But this is only based on inductive effect, not any other effect. So the expected order of basicity for aliphatic amine in gas phase because we are not considering solvent effect. When we are considering solvent effect, that means it is no longer in gas phase. So when it is gas phase, other two effects you don't have to consider. Under that condition, this should be the order of basicity. So when you are solving any question, read the question carefully, whether it is asking basicity order in gaseous phase or in aqueous phase. That information is very important. So R3N, from 3 side plus I effect is operating. When it is 2 degree, only from 2 side the plus I effect is operating, these 2 side. And when it is 1 degree, only from 1 side this is operating. And you can also write ammonia, but there is no plus I effect. Okay, so this should be the order. Minimum basic should be ammonia, based on only inductive effect, not the other two effects. Now solvation effect. So in the aqueous solution, the substituted ammonium cation, why we are saying cation? Because when it is aqueous solution, obviously you have to consider the protonated form. Remember this slide. Whenever amine it is in water, you always have to consider this type of protonated form. So this is the protonated form of 1 degree amine, and if you consider 2 degree amine, then the protonated form will be R2NH2 plus. If it is 3 degree amine and you are considering the protonated form, then it should be R3NH, positive charge over nitrogen. Okay, so now when we are discussing solvation effect, you have to consider the protonated form. Ammonium cations, they get stabilized not only by the plus I effect, but also solvation from water molecules. So now there will be some hydrogen bonding between ammonia and water molecule. The greater the size of the ion, lesser will be the solvation. That means if the protonated amine is very large in structure, water molecules cannot approach very easily. And that is actually the steric effect. So compared to 1 degree, in case of secondary and tertiary, because of steric hindrance, because compared to 1 degree, secondary more steric hindrance, compared to 2 degree, in 3 degree, more steric hindrance. So gradually it is increased. So when it is secondary and tertiary, the number of water molecules, they cannot approach so easily. Okay, because due to steric hindrance, number of water molecules that can approach the protonated amine, that will decrease. So considering these two facts, now see, this is protonated primary amine. It is RNH3 plus. RNH3 plus, there are total 3 hydrogen, 3 water molecules are interacting, 3 hydrogen bonds are there. Then the next one is R2NH2, which is protonated 2 degree amine, 2 hydrogen bond. This is protonated 3 degree amine, only 1 hydrogen bond. So if you simply consider solvation effect, now in 1 degree maximum hydrogen bond formation, that means maximum solvation effect possible. So this should be having the maximum basicity, because RNH3 plus, R2NH2 plus, R3NH plus, all these are conjugate acid. Conjugate acid means if it is amine RNH2, after treatment in water, it is becoming positively charged. Sorry, it is 3. So when it is positively charged, we call this conjugate acid. Remember, when it is acid, you consider the deprotonated form. Suppose you have any acid, HA. After deprotonation, it is A minus. So A minus is called conjugate base. But when it is base and it is protonated, now it is called conjugate acid. Higher is the stability of conjugate acid, the equilibrium will be more shifted towards right hand side, not left hand side. So you will, more is the stability of conjugate acid, we can say higher is the basicity. Now in this conjugate acid, maximum solvation, maximum stability, so the corresponding base, which is nothing but RNH2, that should be maximum basic. After that, R2NH2 plus, what is the corresponding base? That is the actual base before protonation, R2NH. So this should be lesser basicity than RNH2, and then R3N. So if you consider only solvation effect, then 1 degree maximum basic, then 2 degree, then 3 degree. And if you consider only steric effect, then here approach of water molecule is very difficult. But approach of water molecule to protonated 1 degree amine is easy. So from steric effect also the order is 1 degree, 2 degree, 3 degree. But it is not matching with the order that you have seen in inductive effect. Now what we'll do, we'll combine these two effects and the overall result is such. Overall effect of all these three factors in aqueous solution is like this. 2 degree, though it is mostly, there may be some other observation also. So for simple amines like this, 2 degree, 1 degree, 3 degree, and this is simply amine. This is also 2 degree, only alkyl group is different. Now see, 3 degree is coming before 1. So it may vary depending on which type of alkyl group you are taking. So when it is methyl, alkyl group is methyl, that is R group is Me. This is the order. And when R group is Et, now this is the order. 2 degree, 3 degree, then 1 degree. But remember, this is the combined effect of all these factors. Problem related to basicity. Which of the following is least basic? The first molecule CH3CO NHC2H5. So what should be its structure? It is something like this. With nitrogen 1 in H, 1 Et or C2H5, I am writing Et. And then we have COCH3 group. So this is nothing but amide. Not 1 degree amide, 2 degree amide. This is molecule number 1. Then we have simple amine, which is R3N, where R group is ethyl. Then we have option 3. This molecule is like this, CH3CO NH. This is actually urea derivative because, sorry, not urea. Urea is NH2CO NH2, not urea. So this is as if amide from both sides, right? And then we have 2 degree amine. Now least basic means the lone pair availability over nitrogen, that will be least. So where it is 3 degree, and it is also not mentioned whether it is solvation effect or gaseous effect, and that is also not required. Simply consider the lone pair availability. Lone pair availability obviously compared to amide, in case of amine it is high. So 2 and 3 cannot be correct option because here lone pair availability obviously compared to 1 and 3 option it will be high. Now among 1 and 3, in which case lone pair availability is very less. So it is basically this one, because here both side you have 2 electron withdrawing group. So the lone pair over nitrogen, it can take part in resonance like this. So it is really not available. But this type of resonance in option 1 also not possible. But it is only in one side. But in this molecule, it is possible in both sides. That means lone pair availability it is still less. Okay. And here option 1 and 3, one side you have Et. Here both side you have some carbonyl. So Et, it has some type of plus I effect. So still there will be some availability. So among 1 and 3, 3 is least, having least availability of lone pair, and that is why it is least basic. Arrange the following amines in the decreasing order of basicity. Now in these amines, there is some difference because 2 amines are heterocyclic. Heterocyclic means actually all are heterocyclic, and in this case there is some aromaticity. Here also some aromaticity is present, but the last one is basically aliphatic heterocycle. Okay, so this question will try to answer whether there is no solvation effect. You have to consider simply because it is nothing specially, it is not mentioned that you have to answer this in aqueous condition. If that is so, it will be mentioned specifically, but that is not mentioned. So we will simply consider the lone pair availability. So the last molecule, which is known as basically piperidine, here lone pair over nitrogen is maximum available. So 3 is basically maximum basic. But why? What is the problem with other 2? If you consider the second molecule, which is nothing but pyrrole molecule. This is piperidine and the first one pyridine. So in pyrrole, if you look at the ring, there are 2 double bonds. This is not aromatic if you consider only 2 double bonds because 6 pi electron must be present. But if you also consider this lone pair over nitrogen, when it is taking part in resonance like this, So the structure you are getting now, negative charge here, nitrogen is positive. So now it is aromatic. So this molecule, the ring will be aromatic only when the lone pair is taking part in conjugation with the CC double bond. Otherwise it is not aromatic. And any molecule, if it can be aromatic, it is very driving force, because aromaticity, it will always lead to stability. So that is why here lone pair availability is really very less, and this is the least basic. Pyridine is in between. So if you keep 2 at least and 3 at max, that is matching only with option 2. And what is the problem with pyridine? See, here also lone pair compared to 2 more available, but it is not so more compared to 3, because here the ring itself is aromatic. The lone pair over nitrogen is not required for maintaining aromaticity. So from that logic, it is more basic than pyrrole, but less basic than piperidine, because here nitrogen is sp2 hybridized. Lone pair is residing in sp2 hybridized orbital. But in this case, last one, it is in sp3. Now among sp2 and sp3, sp2 S character is high. So this orbital where lone pair is residing, that will be attracted highly. So it is less available because it is residing in sp2 orbital. But in case of piperidine, the lone pair is more available because it is residing in sp3. So that is why maximum basic 3, after that pyridine 1, and then it is pyrrole, which is 2. 3, 1, then 2. The increasing order of pKb for the following mole compounds. Now increasing order of pKb means it is decreasing order of Kb, because remember, when basicity is high, okay, then it means pKb low but Kb high. So basicity and Kb, these two directly related, but basicity pKb inversely related. The first molecule NH2CH double bond NH. Then we have this type of cyclic structure where 3 nitrogen molecules atoms are there. Sorry, it is comma. Don't think it is NH2, it is simply comma. And then we have dimethylamine. Now in molecule C, no resonance possible. Okay. And one thing we know, stronger the base, weaker is the conjugate acid. Now if the conjugate acid is very strong, that means weaker conjugate acid means, don't misunderstand this word. Weaker conjugate acid means it is actually stable conjugate acid, because stable means weaker. If something is stable, it will not be very reactive. So when I'm saying weaker, it is basically meaning stable. Stable conjugate acid means stronger base. So if you have any base RNH2, and now the conjugate acid is R, from RNH2, now it is RNH2 NH3 plus. So conjugate acid is very stable. That means this base is very reactive. Strong is related to reactive. Weaker means stable, less reactive. So strong base will be having high tendency to accept a proton, resulting very stable, or you can say resulting very weaker conjugate acid. Now in case of C, if you consider the protonated form, it is actually Me2 NH2. But in this case, no resonance possible. Whether you consider protonated form or not, resonance not possible. So C is basically least basic. That means pKb value should be maximum. From that logic, any of these options should be correct. Now come to A and B. In both cases, resonance is possible. If you consider molecule A, this type of resonance is possible. Okay, so here only one nitrogen involved in resonance. Even if you consider the protonated form, then also you will see, if you protonate this NH, as it will be NH2 plus, so then also resonance possible. Just let me write. Suppose if you are writing NH2 plus, so in this case also resonance possible. You are getting NH2 plus, double bond C. In this case, it will be neutral. So resonance you can draw structure both in conjugate acid as well as in the original base molecule. But see here, resonance is limited to one nitrogen. But if you consider the second molecule, in this case, resonance is possible involving two different nitrogen. So this is the first structure where this nitrogen, it is undergoing resonance with this. But remember, this is first possibility, this is second possibility. This nitrogen can also take part in resonance. And this structure, it has some analogous of guanidine. In guanidine also same type of explanation is possible. In guanidine, this basic 3 nitrogen structure is there, but cyclic ring structure is not. That is the difference. But here both nitrogen, I mean this as well as the right hand side, both can take part in resonance. You can also consider the conjugate acid and you can draw resonance. So here conjugate acid resonance will be available. So that is why, though here resonance is shown in the original molecule, but you can also consider the conjugate acid and draw accordingly the resonance structure. So because of more resonance, it will be more basic. So among A and B more than C, and among A and B, B is more strong. Okay, but we have to consider pK. If you consider basicity order, suppose in the question if it is asking basicity order, then maximum is B, then A, then C. But you have to find the reverse. That means now C, then it should be A, and then it is B. So that is why option 4 is the correct option. So we have discussed different basic problems, that is basicity related problems. Next class we will start chemical properties, because physical properties are done. So we are at the end of the session. Thank you for listening. We are ending the session here.